Hello learners, in this video we are going to see matched filter. First we will see receiving filter. The signal G of t is received in the receiver and this signal is added with the white Gaussian noise. The resulting signal is given into the linear time invariant filter of impulse response h of t, and then the output y of t is taken from every t sampling time period. The output is taken. The switch is closed for every time period. Okay, this is the receiver model. In this receiver model, it uses linear time invariant filter, which has the simple function h of t. The filter input x of t it consists of pulse signal g of t plus additive white Gaussian noise w of t. X of t equal to g of t plus w of t from the ranges from 0 less than or equal to t less than or equal to capital T. Here T is the observation interval. The pulse signal may represent the binary symbol 0 or 1 in a digital communication system. While W of T is the sample function of white Gaussian noise with 0 means and power spectral density is equal to NR divided by 2. Since the filter is linear, so it will produce the linear output. Y of t equal to G naught of t plus N of t. And G naught of t is the signal output produced by the filter and N of t is the noise component produced by the filter. Here, peak pulse to signal to noise ratio is defined as eta equal to a modulus of G naught of t the whole square divided by E of n square of t. Here, G of modulus of G naught of t the whole square is the instantaneous power in the output signal. E is the statistical operation expectation parameter, and E of n square. E of n square of t is the measure of average output noise power. And G of f is the Fourier transform of known signal G of t. H of f is the frequency response of the filter. The Fourier transform of output function G naught of t is equal to H of f into G of f. If we find the inverse Fourier transform of G naught of t, G naught of t is equal to integral of minus infinity to plus infinity H of f into G of f into e power plus j 2 pi ft into dt. G naught of t is equal to integral of minus infinity to plus infinity g of g naught of f into e power plus j 2 pi f t into dt df. And then the filter output is sampled at every the filter output is sampled at every t time period. The filter output is sampled at every t time period. Then G naught of t the whole square is equal to magnitude of integral of minus into plus into h of f into g of f e power plus j 2 pi ft into df the whole square. Power spectral density of noise, output noise is equal to power spectral density of input noise into square of magnitude of h of f the whole square. So S of L, N of f is equal to N naught divided by 2 h of modulus of h of f the whole square. If we find the error, average power of output noise n of t, average power of output noise n of t is equal to E of n square of t is equal to integral of minus into plus infinity Sn of f into df. If we substitute Sn of f here, then we will get n naught divided by 2 integral of minus into plus infinity modulus of h of f the whole square into df. And Schwarz inequality. Here eta equal to magnitude of integral minus into plus infinity h of f g of f into exponential of j 2 pi f t into df the whole square in divided by n naught divided by 2 into integral of minus into plus infinity modulus of h of f the whole square into df. Here in this is the Schwarz inequality. Here integral of magnitude of integral of minus into plus infinity pi 1 of x into pi 2 of x into dx the whole square less than or equal to the integral of minus into plus infinity. Integral of minus into plus infinity pi 1 of x whole square into dx integral of minus into plus infinity pi 2 of x into dx. Here we consider pi 1 of x is equal to k into complex conjugate of pi 2 of x. Here we consider pi 1 of x equal to h of f and pi 2 of x equal to g of f into exponential of j pi ft. Here Here, the magnitude of integral of minus into plus into h of f into g of f exponential of j 2 pi f t into df. The whole square is less than or equal to integral of that means we split the function two function. One of the function is integral of minus into plus infinity h of f the whole square into df into integral of minus into plus infinity h of g of f the whole square into df. Here, this if we take the magnitude function, this e power j theta is equal to 1. Magnitude of e power j theta is equal to 1. We consider only the magnitude function. Eta equal to z less than or equal to eta less than or equal to 2 divided by n naught integral of minus into plus infinity modulus of g of f the whole square into df. And the optimum filter function h of h optimum of f equal to k into complex conjugate of g of f into exponential of minus j 2 pi f caps t. In time domain function, optimum filter response is equal to h of t is equal to k into integral of minus infinity to plus infinity modulus of g of f into exponential of minus j 2 pi f into t minus t into df. Matched filter. Matched filter, the transfer function is here we consider complex conjugate of g of f equal to g of minus f, and the optimum function h of optimum is equal to in k into integral of minus into plus into g of minus f into exponential because the real signal g of t. So complex conjugate of g of f is equal to g of minus f. G of minus f into exponential of minus j 2 pi f t minus t into df. That means we take the inverse Fourier transform. If we take the inverse Fourier transform, we will get the function is k into g of t minus k into g of t minus t. This is the time domain function. And properties of matched filter. This is the function of matched filter. H of the impulse response of matched filter is h of t is equal to k into g of t minus t. The impulse response of optimum function is uniquely defined except for the delay t and scaling factor k. The waveform of the pulse signal g of t is which the filter is matched. The complex conjugate of Fourier transform of signal is h of the optimum response. H optimum of f is equal to k into complex conjugate of g of f into exponential of minus j 2 pi f t. Here, the peak pulse signal to noise ratio of the matched filter depends only on the energy of the signal and power spectral density of the white noise. Does not depending upon the filter response. To demonstrate this property, G naught of f is equal to H optimum of f into Gf and k into k into complex conjugate of g of f into exponential of minus j 2 pi ft. Here, complex conjugate of g naught of f into g of f is equal to magnitude of g of f the whole square into exponential of minus j 2 pi ft. If we take the inverse Fourier transform, g naught of f t equal to g naught of t is equal to integral of minus infinity to plus infinity g naught of f into exponential of e power j 2 pi f t into df. Here, if we substitute this function here, this exponential term, these two exponential term will cancel. We will get the k equal to integral of minus into plus infinity modulus of g of f the whole square. This function is the energy function. As according to the Rayleigh energy theorem, the integral of squared magnitude. The integral of squared magnitude spectrum of pulse signal with respect to the frequency is equal to the energy signal. So energy is equal to integral of minus into plus infinity g naught of t the whole square integral of minus into plus infinity magnitude of g of f the whole square into df. So g naught of t is equal to g naught of t equal to k into e. So here E of n square of t is equal to k square n naught divided by 2 integral of minus infinity plus infinity mag of g of f the whole square. This g of f the whole square is equal to integral of minus infinity plus infinity g of f the whole square into df is equal to e. So it is e naught expression of n square of t is equal to n square of t equal to k square n naught E divided by 2. Yeah, the maximum energy, peak energy to signal ratio is equal to energy to signal to noise ratio. Peak energy, peak energy to signal noise ratio is equal to E of k square divided by k square n naught E divided by 2. Here this E and this E get cancelled. We will get 2E divided by n naught correlation filter. The optimum correlation filter, the optimum filter of the additive white Gaussian noise channel, and for the case when the transmitter signal S1 of t, S2 of t up to Sm of t are equally likely is called correlation receiver. This correlation receiver consists of two subsystems, detector and maximum likelihood decoder. This is the diagram for maximum likelihood decoder. In this maximum likelihood, in this detector, in this director, it consists of m number of correlator. This is the correlator. This correlator consists of a product plus integrator. Okay, this is the it consists of n number of correlator with the orthonormal basic function pi 1 of t, pi 2 of t, pi n of t. It will generate the it has the bank of correlator and on the received signal of x of t. It operate on the received signal of x of t and provide the absorption vector x. This is the maximum likelihood decoder which operate the absorption vector which operate the absorption vector and produce the estimate value of m transmitter signal, and it has the inner calculator. This inner product calculator, it is the product of S of t plus accumulator, and here the different kind of energy is given, and depending upon the output value, the transmitter signal is estimated.